Hello there. If you do anything with microprocessors or STM32 blue pills, things like that, you have probably already become a fan of Ralph Bacon's channel, and you may have already seen the latest video he did, which is called Your Arduino as a State Machine. You can see an image of his splash screen behind me there. This is an awesome little short video where Ralph talks about using other means of delaying a program other than the delay function, because delays are really bad if you want to do multiple things in an application. And apparently this is going to be his first step toward multitasking, and I can't wait to see the rest of the videos he produces. But right now I want to show you what I have done for our use in our pinball machines. Now there's a lot of ways to do this, and there's a lot of reasons to do it one way versus the other way. I've had my reasons, and so I'm going to kind of show those to you today. I'm going to show you a little bit of what my design ideas were and why I built it the way I built it, and then I'll take you through the code of a very simple blink routine to show you how this works. So let's go ahead and get right into it. So to accomplish building an application that has multiple events that need to happen and not using the delay function to delay each of those things you need to do, I developed myself a simple time-based queue for Arduino or STM. And so I want to step you through a quick little slideshow here. It's only about 8 slides, and it's going to talk about what I wanted to accomplish and what I did. So my design goal was I wanted this to be really easy to use. I wanted it to run without modification on different platforms like Arduinos and STM Blue Pills, which are the two processors we use the most. I didn't want to use any plugins like malloc and stuff like that to allocate space for the queue. So I just wanted to assign a static storage area that the queue would be used in. Now, this becomes a little problematic depending on how much memory you have. If you allocate too much queue space, you won't have any room for your program. So you need to watch, depending on which processor you have, you'll have different amounts of dynamic memory that you can use, so you need to allocate that correctly. And I didn't want to use any timers or interrupts and stuff like that because they vary from processor to processor, and you'd have to have individual unique routines for that. So I wanted this to just be a simple polling architecture that would go through the queue, poll each of the queue entries to see if anything was ready to be executed, and then execute it. So my queue entry, which is 10 bytes long, starts off with a time for the event to mature. And basically what you do is you take the current time and add however many milliseconds in the future you want this event to occur, and you store that in the event mature variable. Then you put in a procedure pointer. So when this event matures, what procedure do you call to be executed? And then you pass 3 arguments that you have the option of using or not using. So you have a 1-word argument and 2 single byte arguments. And that's the entire makeup of the queue. Now, there are only 2 routines in this queue processing. There's the AddEvent, which puts an event in the queue, and there's a CheckEvent to see if any events in the queue need to be executed, and if they do, you execute them and then clean up the queue. So for an AddEvent, you have a Boolean event. It does return a true or false, where you call AddEvent and you put the time the function you want to call, and the three arguments that can go with it. So what the AddEvent routine does is it checks to ensure that there is space available in the event queue. If it does, it adds the queue to the event. It increments the max queue counter. It returns true if that was successful, and it returns false if it was unsuccessful. So here is an example, and I'm going to show you the code where this came from in a little bit. But you add event millis plus 1,000, so you're giving a 1 second in the future time, and you're going to run the function blink LED, and the first variable is the number, the time for the next iteration after this iteration. So this iteration is 1,000 milliseconds, and the next iteration is going to be 1,000 milliseconds in this example. The second variable, which is a byte variable, is passing the number of the pin on the Arduino that will be toggled. So that's it. So you're putting an event on the queue that says, in a second, jump to the routine blink LED, toggle the built-in LED pin, and then re-queue this for 1,000 seconds again in the future. And I think that's all what I said down here. I did not use the last byte variable for anything, so you just toss a 0 in there. You have to define it both here and in your routine that you call. And I'll show you that in a little bit. So the check event, the first thing it does is check the event counter to see if there are any events in the queue. If the event counter is 0, there's nothing to do and you just leave. If there are events in the queue, you scan through the entire queue, starting with the oldest posted one to the latest posted one, to see if any of them that the mature time in the function is less than the current time. If that's true, then this event has matured and needs to be executed. So you transfer to the pointed to function and pass along its 3 arguments. And when that function is done, it returns back to right where it left, which is in this queue routine. And the queue routine will delete that queue entry, so it doesn't get executed a second time, and then exit. Or actually, it'll continue running through the rest of the queue, and then it'll exit. And that's it. That's how the whole thing works. So here is an example of a blink function that you might call from this queue routine. So you describe the blink function as a void, and this has to be a void. You can't return any variables back. So in this example of the blink routine, you come in to this routine from the queue, bringing along the word and 2 byte arguments that were stored in the queue. You digitally write out to the pin specified in EB1 the contents of the pin specified in EB1 inverted. So that toggles that pin. And this is the same function basically that Ralph used in his code to toggle his pin. And then you queue up another event of this same event. So you send out with the time millis plus whatever you passed in EW1. So that could be different. It doesn't have to be the same number. In my case it is, but it doesn't have to be the same 1,000. It could have been 500 to toggle it again. But whatever's in EW1 will be added to millis. You want to execute this blink routine again. And again, that doesn't have to be the same, or you don't have to even do an add event if you don't want to. If you had a one-shot event you needed to do, you do it and you leave. If you want to do it over and over again, you have to re-queue it at the end of the event. And you pass along the pin number that's in or the time in EW1 and the pin in EB1, and you send it back. You send that back to the queue. That's the entire blink function. Now, this routine can blink multiple LEDs at the same time, multiple rates at the same time. So now let's look at an actual Arduino code to see how this little test program is put together and what variables and stuff I use. Now, I want to start by saying I am a horrible programmer and I almost don't understand how this works. I actually hunted the web to figure out how to accomplish what I needed to accomplish. It was a long time ago and I don't have any references to where I found the information. So thanks to all the programmers out there who have put this information out and helped me develop this code. None of it is mine. It's pretty much all copied from other people, but I don't know, unfortunately, who those other people are. But let's start off with this little program. Actually, I want to say one other thing. If you watch the Ralph Bacon video, and I highly recommend that you watch that before you watch my video, he talks about using variables and not using, or using local variables and not using global variables because it's a bad programming technique. Well, I use global variables. Again, I'm a bad programmer, and I don't know any other way to do it, to be perfectly frank, so that's the reason I do it. If you know a better way and you want to tell me, please do. I like criticism, and I like to learn from what other people know, so if you know anything, let me know. But anyway, I start off by defining the max Q amount as 100 Q entries. Now each entry is 10 bytes, so that is just about a kilobyte of memory. In something like a regular Arduino, you only have 2 kilobytes of memory, so if you made that 200, you'd already be out of space. So you got to be very careful. I'm using an Arduino Mega for this particular test. So, and I think I still have that set up for that. Nope, I checked the STM32. So let me set my board to the correct board. Arduino Mega. So there you go. So I'm using an Arduino Mega. So when I compile this, you'll see how much memory and stuff is available. And then I set up a couple of those global variables I was just talking about. Use Q, so that's used by the routine to see how many Q entries I've put in. And as long as use Q is smaller than the max Q, you can add Q entries. And then for diagnostic purposes, to see if you have a pretty complex program, you might wonder, well, how many Q entries am I using on an average day in this program so that I can maybe more accurately allocate the amount of space I need? So I tossed in the function max Q ever used, and the Q routine will, as it's adding things to the queue, will check to see if I've exceeded the max Q ever used, and it'll save that so I can print that out every 10 minutes or so to see what my max Q counts are. So the first thing I need to do is define a couple of functions and structures that I use to make this all work. So I do a type def of type void for the value. It's a pointer to void function with no return. And this is the value that I'm going to be storing to point to the function that I want to execute. And it's going to use the those arguments, EW1, EB1, and EB2. Then I create a structure. And the structure is the overall construct of the queue entry. So the first thing is a long mature event, and in Arduino and STM32, that's 4 bytes. The void function no return, which is a 16-bit pointer, and then a union, and I use this union because sometimes I want to describe the three arguments as three separate arguments, and sometimes I want to describe it as just one 32-bit word that I can just move together. So I union those two things together, and then I can either refer to them as event data or the variables. And if you don't know how to do unions, I can't really explain it well, but there's a lot of great documentaries out there about unioning data together when you do a structure, and it makes perfect sense. So once I've defined those two things, by the way, I did this one time and I've placed it in a library in a header file, and I never do it again. And I just include the header and it works. So same thing with my add to queue and check queue routines. Those are all in the library. I don't have to put them in my code. So the first thing I have to do is I have to create that timer queue storage location. So I allocate the max queue amount of the event entry structures and call it time queue. So time queue is where I'm going to store the name that I'm going to store my queues in, and it is of this construction, and it has that many entries in it. Okay, so that's it. Now, the setup is really dirt simple in this program. I enable serial because I'm printing out stuff so you can see it. I print out a start, and I print out the number built-in LED just to see what it is. It's 13. Everybody who uses Arduinos knows it's 13, but I'll tell you. And then I add two events to the event queue. And again, this is in setup I'm doing this. I add a 1 second delay to blink the LED, and I add a 10-second delay to print the max queue ever used. And in the loop, there's only one thing: check events. So it checks events, and then it checks events, and then it checks events. You can put other things in this loop, but you don't have to if you make everything event-driven. So now I have my two routines. But before I go to those routines, let me step down to the AddEvent function, and that's right here. And as you can see, it's a fairly small piece of code. It's whatever, about 15 lines or something, including comments. And as you can see, I have that defined layout up here: void function return procedure with the three variables. And this routine is called AddEvent. So I do an AddEvent and I put those things in there. So let's look at the AddEvent function. It, as I said earlier, it's a Boolean, so it returns a true false. You add the event with the mature time, pointer to the procedure you want executed, and the three arguments that you will pass to that procedure when you execute it. So the first thing it does is it checks to see if we've exceeded the max queue, and if we have, it returns false. Otherwise, it just checks to see if the amount of queue used is exceeding the max queue ever used, and if it has, it increments that so that the max queue ever used keeps track of whatever the highest watermark is for what we've been recording or what we've been storing. And then it adds to the time queue the pointer of whatever the use queue is, which will be the highest one in the queue. It adds the event mature, the procedure pointer, the three variables. It increments the use queue, so it's now pointing to the next location, and then it returns. And that's it. Very quick, just a few instructions. It puts the thing on the queue, and then you're ready to check it every time you run the check events. So let's look at the check events. It's actually a fairly short piece of code also. So the first thing it does is it checks to see if there's anything in the queue. Obviously, there's nothing to check if there isn't. So if there is some queue used, then it goes down and it says for, so it just sets up a for loop that's going to run through each of those queue locations. And then it checks to see if the current time is greater than the time that this thing matured. If it is, this event is mature. So if it is, it takes the time queue pointed to by eyes procedure pointer and passes the time queues EW1, EW2, and EW2. That executes that function passing those variables. And then once that function returns, it comes right back to here. So it checks to make sure that this wasn't the last entry in the queue. And if it wasn't, it moves everything up one location. So it starts J off equal to I, which is pointing to the next location in the queue. Well, as long as J is less than use queue, it increments J and it moves time queue J from time queue J plus 1. So it just moves up one location, increments J, moves up one location, increments J, so on and so forth until it's all done, moving everything up. It doesn't delete the one in the last location. It doesn't care. The counter makes sure that you're never going to execute that. So it just leaves the last one there, but it moves it also up into one location higher. Then it decrements the amount of used queue to say that we now have one less unit. And then this loop ends and we're still in the for I equals whatever. So now it checks the next location. I actually believe this might skip over one location, but that really doesn't make any difference because then as soon as this is done, it just starts over again and runs it back down from the top. So it'll find it next time if you have two that have expired at the same time. But that's it. That's how you execute it. Now let's go look at the actual blink LED routine. And actually you've seen this one already because this is the example that I brought up. But you have blink LED with the three variables that you pass. And it takes whatever is in EB1, which is a byte number, and it's going to be the number 13. So it takes, it digitally writes to pin 13 the contents of a digital read from pin 13, which in essence toggles pin 13. And then it adds a new event using the time, current time plus whatever is in EW1, which was 1,000. So it'll have 1,000 in it again. And we're also going to pass 1,000 again as the variable for the time after this, and the byte to execute. And that's it. Now let's take a quick look at the print max queue. So every 10 seconds, print max queue used should be run. And print max queue just prints out max queue ever used, max queues of the amount of space you've allocated, and then it adds the print max queue event to the queue, and it puts the same time, 10 seconds, in the how long should it be before we execute, since that is what we put. If you look here, we put 10,000 in EW1, so 10,000 will be what's passed. And that's everything. That's my whole program. There's nothing else here. So let me run this real quick and show you what it looks like when it's running on the well, I'm going to upload it. It runs okay. It uploads. Just for looking at the amount of space used. So as you can see, it used 1,256 bytes, or 15% of the memory on the Arduino Mega. And 1,000 of those 1,256 bytes are the Q locations. So it's a significant amount. So let me open up the serial monitor. And you can see it said it started. It was using pin 13. And that find is left over from defined. That's from the old stuff. So now it's running every 10 seconds. It's putting out the fact that I've only used 2 Q entries. Even though I'm resending these Q entries all the time, it takes one off and then puts another one back on. So the maximum number of entries ever in the queue is only 2. So for this application, you know, I could probably safely turn it down to just 2 entries in the queue, but that would be stupid to do that. So, you know, if I saw this after using a program for, you know, several hours at the maximum entries were ever only 2, I'd probably crank the queue size down to 25 or something like that instead of 100, because it's just wasting. Of course, I might not, because I got nothing else to do in this program. But anyway, so it says that it's using 2 of 100, and that's it. Okay, I'm just going to bring up the little Mega, and you can see right here the LED is blinking at that 1 blink per second rate that I programmed into my code. So I'm going to go back and show you what it would look like if I change some of those variables. So what if you wanted a different on time and off time to blink the LED instead of just toggling it on and off at a fixed rate? In order to do that, you would need 2 routines. You would need a turn on routine and a turn off routine. Okay, I have made the modifications. I have a blink LED on and a blink LED off function. And when you call the blink LED on function, it sends a high out to whatever the pin is on EB1. And I left the old comment. It doesn't toggle, it turns it on. And then it adds an event to do a blink off, which however much time you said you wanted it to blink on. And then the blink off is going to pass 100. So it's going to turn it off in 100. So 100. So in this case, what did I have the calling thing on? 500. Okay, so so the on routine, I know this gets a little confusing, but you'll get it after a while if you play around with this for a while. So the on routine is going to take the value that was passed in EW1, which was 500, and it's going to add it to millis, and it's going to schedule, so it's going to turn it on and then schedule an event to turn it off 500 milliseconds later. And in the scheduled event for 500 milliseconds later, it says, I'm sorry, I'm on the wrong routine. So it's going to turn it on, and it's going to schedule an event to turn it off 500 milliseconds later, which is what's in EW1, and it's going to tell it that it should end that 100 milliseconds later. So the turn it off routine, blink off, toggles it low, which turns it off, and then it adds an event that adds EW1, which is now just 100, to the turning it off, and it says blink the LED and pass it 500 to turn it back on 500 milliseconds later. So this is going to make a turn on 500 milliseconds, turn off 100 milliseconds, turn on 500 milliseconds, turn off 100 milliseconds. And it's just going to toggle back and forth because they call each other. So blink off calls blink on, and blink on calls blink off. And that's it. So let me upload this. And I'll open the task thing to show you that it's still only using two queue entries. And let me just drag myself big here just to make this quicker. So if I bring this up to the camera, you should be able to see the LED right there, blinking on for 500 milliseconds and off for 100 milliseconds. So that's how you would make an asymmetric blink capability. So that's it. Once you've set up these primary functions, all you need to do is enroll the queue entries and then check to see if any of the queue things have expired. So I've decided to see if I can figure out how much time the queue takes to process, how much that's going to add to your program execution time. And I've been playing around with this for a while. As a matter of fact, it's the next day. So I'm back here still recording. And what I have done is made a few changes to my program. So let me step you through those and show you what those changes are. So to start off with, let me go up to the very top. I still have 100 entries in the queue. But I've added two unsigned long variables, time 1 and time 2, because I'm going to record the time when I start and when I stop the execution, and then I'm going to take the difference and show that to you. Now, initially, when I did this, I used the millis timer, and the time was always under a millisecond. So I changed it to the micro. So this is going to be time in microseconds to run through the loop. So the minor add I made in the loop timer is every time the loop starts, what used to be in time 2, which was the previous time through the loop, I put in time 1, and then I set time 2 to the current micros, and I do the check event. Okay, so that's the change to the loop. Now to the change to setup, I decided that I wanted a bunch more entries in the queue. So I added 90 more entries. You'll remember from a few seconds ago, there were 2 entries that were being used for the other 2 events that I had put in. So I'm going to put in 90 more events. And I decided to make these events of varying times. So I made a new event called junk. And I start off at 5 seconds. Because I'm multiplying it by I, the first one will be 5 seconds. Actually, the first one will be 0, and it'll terminate before you even see this. But the second one will be 5 seconds later, and then 10 seconds, 20 seconds, or 15 seconds, 30 seconds, and so on. So as we're watching the printout, it's going to show you how much time it's taking. Actually, I think I will go ahead and change the printout to, yeah, every 5 seconds it'll print out how much is in there. Then the junk routine you will see down here, where I put it. Did I miss it? There it is, junk. It's an empty routine, so it does nothing. It just does nothing. So when it ever gets executed, all that does is just take the queue entry off of the queue, and the rest is just a matter of the time it takes to run through the queue. So let's upload this. By the way, I haven't tried this yet, but I think I'm going to stick this in an STM32, which is a much faster processor, and see how much time the queue takes in there. Okay, that looks like it uploaded successfully. I wasn't watching. Let's turn on the display and see.
I don't know that.
Thank you, Alexa. So as you can see, as those queue entries are being used up, the amount of time it takes to go through is decreasing. So with 91 queue entries, it only took just a little under 300 microseconds to run through that loop. So that's really not a lot of horrible overhead for this kind of event processor. So I'm very happy with that. And as you can see now, I'm down to 80 and we're at 256 microseconds. So I'm going to let this run, but I'll speed it up and we'll see what it's like when it gets all the way down to 2. Actually, I don't want to wait that long. Let me change this to be every 1 second instead of every 5 seconds. Actually, I'm going to make it every 500, so it'll step down really quick. And let me change this to print out every 2 seconds. This should be a lot faster. Oh, you know what? I forgot something. Hold on. I changed this to print out every 2 seconds, but I need to change it where it re-queues also. Okay, so we'll change that to every 2 seconds also. Upload that. Okay, that's better. So it's stepping down pretty quickly. This should dwindle down to just 2 entries left, and then and there you go. So with 2 entries, it's somewhere between 16 and 20 microseconds of delay. So typically when you're running this in the programs that I run in the pinball machine, I normally see max queue entries at the most at somewhere around 20-25 entries. So so really it's just no real time in general. But give me a second and let me put this into an STM32 and we'll see what it looks like running in there. Okay, I plugged in my STM32. So you can, while that's running, I'll just hold up my little microprocessor here so you can see that this is indeed an STM32 that's running. You can see the blinking LED on it. That's working fine also. So without any changes to the code at all, I was able to run this on 2 different processors. And you can see on this one, because the STM32 is so much faster, there's only 2 or 3 microseconds, excuse me, there's 2 or 3 microseconds of delay on the STM32. So really no problem at all. And even, let me stop the scrolling and see if I can get back to the beginning of this. So when I kicked it off, it was only using 41 microseconds with 88 queue entries in there. So yeah, that's really not much at all. So I think that's going to end what I'm going to be recording here today. I'm just telling you that if you need to have the ability to easily add timed events, setting up a queue like this is one way of doing it. I can't wait to see what Ralph is going to do in his. Probably going to be tons better and cleaner, so you guys need to go over to his channel and watch what he does. And I'll put a link to that down below. So that's it. Thanks a lot for watching. You guys have a great day.